All right, today we're going to tackle a really big question. Literally, we're going to figure out the absolutely crushing pressure that exists at the very center of a planet. And we're going to do it by working through a classic physics problem that beautifully shows how gravity itself is what holds a world together. Let's dive in. I mean, just stop and think about that for a second. Every single atom in a planet is pulling on every other atom, all dragging everything inward toward the center. It's an unbelievable amount of force all trying to make the planet collapse. So, what stops it? What's pushing back? That is the fundamental question we're going to answer today. To answer a question massive, we can't possibly track every single particle. That would be insane, right? So what do we do in physics? We build a model. We create a simplified, kind of idealized version of the real thing that still captures all the important physics. It's one of the most powerful tricks we have. And for our model, we're going straight to a classic source, problem 1.216 from I.A. Irodov's Problems in General Physics. Now, if you've ever studied physics, you've probably heard of this book. It's legendary for its challenging problems that really make you think. By solving this one, we can build a formula from scratch that describes the pressure inside any uniform planet. So here's our big simplification, our main assumption for the model. We're going to pretend the Earth is a perfect sphere where the density is the same everywhere. Now, I know what you're thinking. That's not true. The Earth has a dense core, a mantle, a crust, and you're absolutely right. But you'd be amazed how close this simple model gets us to the real answer. It really shows you the power of starting with a good first guess. So back to our big question, what stops the planet from collapsing? The answer is one simple, beautiful concept: equilibrium. It means that every single force is in a perfect balance with another force. Let's break down exactly what forces are in this cosmic balancing act. I want you to imagine a super thin, spherical layer of rock somewhere deep inside the planet, kind of like one layer of an onion. It's definitely being pulled inward by gravity, but at the same time, it's being pushed outward by the intense pressure of all the compressed stuff beneath it. For the planet to be stable, those forces have to be in a perfect deadlock. We call this hydrostatic equilibrium. Okay, let's nail this down because getting this part right is the key to everything. Our imaginary shell feels three main things. First, there's a powerful outward push from the high-pressure material below it. Second, there's an inward push from the material above it. And third, there's the inward pull of gravity acting on the mass of the shell itself. For the planet to just sit there and not collapse, that single outward push has to perfectly balance the two inward forces combined. All right, we've got the physical picture locked in our minds. Now it's time to translate that picture into the language of math. But don't worry, every single step we take with the equations is going to follow directly from the logic we just laid out. This is how we build our formula from the ground up. Now, before we write down our main equation, let's talk about a super common pitfall. This is a question that trips up so many students. When you're inside the planet, say halfway to the center, how much mass is actually pulling you down? Is it the whole planet? This is a great question. And the answer is just incredible. It's one of the most elegant results in physics. Thanks to something called Newton's shell theorem, it turns out that all the mass outside of your position, all those layers of rock above you, pull on you in all directions in a way that perfectly cancels out. Their net gravitational pull on you is zero. It's wild, but it means we only have to worry about the mass of the sphere that's beneath our feet. Okay, let's get our cast of characters straight so the math makes sense. dP is the tiny little change in pressure as we cross our imaginary shell. dm is the mass of that thin shell. Gr is the strength of gravity at that specific depth. And the most important one here is mr. That's the mass enclosed within our radius r. Remember, that's the only mass that's actually pulling us down. So when we actually write down that balance of forces using these terms, the outward push equals the two inward forces, we get something called a differential equation. It's a fancy name, but all it really is a rule that connects the tiny step-by-step change in pressure to the local density and gravity. And there's a negative sign in there, which just tells us that as we go deeper, as our radius gets smaller, the pressure has to get bigger. Makes sense, right? So if we have an equation for a tiny change, how do we find the total pressure? Well, this is exactly what calculus was invented for. We use a tool called integration, which is basically a super-powered way of adding up an infinite number of those tiny pressure changes, one layer at a time, all the way from the surface, where the pressure is basically zero, down to the very center. So we follow that logical path, we set up our physical model, we translate it into the language of calculus, we turn the mathematical crank, and what pops out on the other side is our final, elegant formula for the pressure anywhere inside our model planet. And there it is, the pressure P at any distance r from the center. Now I know it might look a little messy, but it's beautiful. Look at that term in the parentheses at the end. See what happens if you're at the surface, where your distance r is equal to the planet's radius r. That whole term becomes 1 minus 1, which is 0, and the pressure at the surface is 0. So our formula works. It's perfect. Okay, so we did the hard work, we started with a huge question, we built a model, and we derived a powerful equation from first principles. Now for the payoff. Let's circle all the way back to the beginning and finally answer our question about Earth. Let's use our brand new formula for the most extreme point possible, the dead center of the planet. So at the very center, what's our distance r from the center? Well, it's just 0. And that makes the math in our formula super easy, and it's going to give us the absolute maximum pressure our model can predict. And now for the really fun part. We just have to plug in the numbers. We'll use the standard values for the Earth's mass, its radius, and of course, good old big G, the universal gravitational constant. You punch all that into a calculator, and what do you get? Whoa. The pressure at the center of our idealized Earth is about 1.8 million atmospheres. That is 1.8 million times the pressure of the air you're breathing right now. It's an almost unimaginable force, and it's all generated by the planet's own gravity pulling in on itself. So what's the big picture here? What did we really learn? First, we learned that we can tackle incredibly complex problems by simplifying them into a manageable model. Second, we saw that by understanding the forces on just one tiny little piece, our imaginary shell, we can figure out the behavior of the whole system. And finally, we saw that calculus isn't just some abstract math, it's the language that lets us connect those tiny pieces to the big picture. But of course, we're not quite done. Remember our big simplification at the start? We assumed the Earth's density was uniform, but we know the real Earth has a super dense iron core and a much lighter crust. So here's a final thought for you. How would that change the answer? Do you think the actual pressure at the center is higher or lower than our 1.8 million atmosphere estimate? That is the next step in making our model even better.